balance of energy rate. Right. So, right, our biblical equation, for those who have just found a new religion, is this. And this happens between two instants in time, t1 and t2, right? Let's say over a time delta t. So I'm going to divide these guys by delta t. I'm going to do the good old trick that say, well, let's now assume that delta t is really, really small, right? Tends to 0, becomes an infinitesimal. So these guys are going to turn into this new equation. It's more or less the same thing. What are the units of Q? Yeah, I hear joules per second, but I want the proper name. Watts, right? This is watts. And you know watts because you pay for the kilowatt hour at home, and you measure electric motors in watts, all the light bulbs in watts, all that type of stuff. So, same story. The only difference is now instead of doing this bulk analysis between two stages, now this is per unit time. So this how many watts are coming in, how many watts are going out, how many watts I'm generating, how many watts I'm storing. So rate of heat stored, much like before, we're going to spend the whole class on Q in and Q out. In this first week, I want you to master the Q stored. So if you bear with me for a quick second, we said Q stored, right, was M2 I2 minus M1 I1, right? So if I divide this by delta T, I'm going to end up with Q stored equals trivial, looks trivial, amazingly powerful equation, because this equation lets you calculate heat balances in open systems, closed systems, phase transformations, no phase transformation, whatever you want. I'm going to do the last thing before we leave. Is for a system that is closed and no phase change, right? Q stored equals mass, constant or not? Constant, because it's a closed system, but only because it's a closed system, okay? All right? di dt. Now I'm going to do something I know you love. That is a chain rule, right? That is, and I'm going to say instead of di dt, I'm going to say di d big T, the variation of enthalpy with temperature, a variation of temperature with time. What's the name of this guy here? Heat capacity, right? That's a specific heat. So what we got is that Q stored is mass times specific heat times the rate of change of temperature. So powerful, because this says if you can measure the change in temperature, for example, you go to Home Depot and you buy a $20 amp meter that has a temperature sensor. I have one of those. You know the mass you have, and you know the CP, the specific heat, because you bought the book or you found the book in whatever, right? And now you can calculate energy from the measurement on your $20 meter. Very powerful, very powerful. As we were finishing last class, we talked about rate of heat stored. Right now, this is going to be watts. and we said the definition, and this is a definition, right? And I said, if we have a closed system, what does it mean, having a closed system?
Only energy passes the...
Right, but the mass doesn't, right? There's no mass flow through the boundaries, okay? That's what matters. So in an open system, do I have an open control volume? No, the control volume is always closed. When we talk about an open system, it means that there is mass that comes in or out of our closed control volume. So the control volume can be infinitely large. So you can say one end is in infinite, but it's always closed, the control volume. All right, so if we said for a closed system, right, this is all a review. We have dm equals 0, right? So we can say Q stored equals mass times di dt. This is true. But it doesn't say so much. Because the cool thing is if we do the chain rule, right? I know you love it, but we're going to go quick over that. So we say di, and here we have a dt, but I multiply and divide by this differential temperature. Now things start to speak to us. It's not about the math, but the thing speaks to us. Why? What is this? What is this? Specific heat, exactly. This is specific heat. This is tabulated. What is cool about the specific heat? Why do we gain anything by giving a name to this derivative?
You can estimate it to be constant.
Right, it's very, very close to being constant. So we tabulate it. So for example, water is about 4 joules per gram per degree C. Actually, that's a calorie, 1 calorie. It's more or less, right? And then if you look at the book, you're going to see a table that says it's not exactly constant, and ask me if I care. It's going to be fine, right? But if you want to go fancy, you go fancy. And if you want to do the integral, I have an example doing the integral in the notes you already have, right? So we have mass times specific heat times, and this is heating rate or cooling rate. This is what even you see in your house when you come in from vacation and your house was like maybe you had your house at 12 degrees or something. You turn on the heat and you see the temperature going up so many degrees per minute. That's it. Very cheap, very easy to measure. C, tabulated. And just to go one more step, mass we can divide as density times volume, right? So we can say this is volume, not velocity. Sorry. Sometimes you have this density times heat capacity together tabulated, right? And this would be volume. Okay, I have not taught you anything new so far.